Molecular geometry. So we're going to learn how to draw Lewis structures for covalent molecules. And with these, since they share, you're going to have shapes that form. So we're going to learn how to make the shapes and tell which shapes they are. So here are the rules for drawing molecules. Obtain the sum of the valence electrons from all the atoms. Form bonds between the center atom and the outer atoms. The least electronegative atom goes in the center. So you need to remember your electronegativity trends. And then distribute remaining electrons to satisfy the octet rule, which is everybody wants 8, right? Except for hydrogen, he only wants 2. Ions. If the charge of the molecule is negative, the number of electrons in the charge will be added to the sum of the valence electrons, right? So if it's negative, that means they've gained electrons. If the charge of the molecule is positive, the number of electrons will be subtracted from the sum of the valence electrons. That means they've lost electrons. Resonance. If more than one Lewis structure is possible, then the molecule is said to have resonance, right? We could have put the double bond here, or we could have put it here on this oxygen, or here on this oxygen. And when that occurs, you have to draw all the resonance structures. Dipoles. The more electronegative the atom, the tighter it will hold the electrons close to the nucleus. And that way, it creates what we call a dipole. So carbon, so if we look at this molecule right here, carbon, we have 3 hydrogen, which aren't very electronegative at all, right? It goes up and to the left. Fluorine is the most electronegative element. So he's going to hog all these electrons that they're supposed to be sharing, right? So you're going to have a dipole moment. And we indicate a dipole moment with an arrow. It looks like this, an arrow pointing towards where the electrons are, and then a little plus sign indicating that this side of the molecule right here is a little positive because all the electrons are hanging out over here. So if you look here now at water, oxygen is more electronegative than the 2 hydrogens, so water is polar. Now with carbon dioxide here, oxygen's going to hog electrons on this side, and oxygen's going to hog electrons on this side, but overall, the molecule is non-polar because the dipoles cancel each other out, so it's equal and opposite. All right, so a polar molecule always contains polar bonds, but some molecules with polar bonds are non-polar, like I said with carbon dioxide. A molecule in which the bond dipoles do not cancel each other out is a molecular dipole. So if you look here at carbon tetrachloride, if you look at just one bond, carbon to chlorine, that's a polar bond. Chlorine's more electronegative than carbon. But since there's 4 and they're in equal and opposite directions, this molecule is nonpolar because they all cancel each other out. Here, this is ammonia. It has this lone pair. So that means this molecule overall is going to be polar because these little tiny hydrogens, really a lone pair is huge, it's more like this with the 2 electrons. So this is going to be a more electronegative area than these tiny little hydrogens. All right, formal charge. So a way to help determine if a structure is correct is calculating its formal charge. So if we're going to calculate the formal charge of nitrate, maybe this isn't, well, it's NO3, there's no ion. So I'm just going to, let's see, we've got nitrogen, and we have 1, 2, 3 oxygen. And I'm going to label these, that's a 2, so we know this, we'll say this is 1 oxygen, number 2, and number 3. So nitrogen normally has, this is the equation right here, has 5 valence electrons minus half of the bonding electrons. So each line means 2 electrons. So 2, 4, 6, 8, so half of those is 4. Minus the lone electrons. Well, there aren't any lone electrons, so 0. So nitrogen's formal charge is 1. And really, for a structure to be correct, you want everyone to have close to 0, a 0 formal charge as possible. So 1's okay. So let's do oxygen. Oxygen normally has 6 valence electrons. We want to do half of the bonding electrons, so minus 1, minus the lone electrons. 1, 2, 3, 4, 5, 6. Minus 6. So that is negative 1. Okay, that's okay for oxygen. It's a very electronegative atom, so a -1 charge is okay. So let's do oxygen number 2, 6, half of the bonding electrons, so 1, and it's got 1, 2, 3, 4, 5, 6 lone electrons. It's also -1. All right, that's all right. Third oxygen, 6 valence electrons, 1, 2 bonding electrons, minus 1, 2, 3, 4, which is 0. So that's good. So overall, these are pretty close to 0. So this, I would say, is the correct structure. Now, if you drew a structure and you calculated like a 2 or a 3, then you probably drew the wrong structure. Shape. So, shape. The valence shell electron pair repulsion model, or VESPER for short, is based on the number of regions of high electron density around a central atom. And it can also be used to predict structures of molecules or ions that contain multiple bonds or unpaired electrons. So here we go. Here we've got these two shapes right here. They're called linear because they're in a straight line. This is bent, and it's bent because we've got 2 lone pairs there. This one is trigonal planar, and y'all need to know these shapes. This is trigonal pyramidal because there's a lone pair that pushes these down. Trigonal pyramidal. It's really hard to write with the stylus. Okay. Here, this one is tetrahedral. And this one is trigonal bipyramidal. Bipyramidal. I have a website down here if you want to look. They have these animated in 3D and they kind of rotate for you and give you more examples if you want to see that. All right, so let's do an example. Let's draw, this is phosphate. So we need to calculate all the valence electrons. So let's see, phosphorus has 5 valence electrons, and we've got 4 oxygen, and each oxygen has 6 valence electrons. And since this is an ion, we've got to add these 3 electrons in. So 24 and 8, 32? 24, and yeah. All right, so we've got 32 valence electrons to work with. We can't use any more than that. We can't use any less. We've got to use exactly 32. So phosphorus is going in the middle because it's the least electronegative atom. And then since I've got 4 oxygen, I'm just going to start bonding the oxygen to phosphorus. All right, now let's see how many I've used up. I've used, each line, remember, represents 2. So 2, 4, 6, 8. I've used up 8. So then I'm just going to start adding lone pairs. Phosphorus is happy. He's got 8 around him, but each one of these oxygen wants 8 too. So I've used 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, so I've used all my electrons. Each element has 8 electrons around it. That means everybody's happy. And since this is an ion, I need to put brackets and the charge around it. Okay, ammonia. So we're going to add up the valence electrons. Nitrogen has 5 each. Hydrogen has 1, so 8. So nitrogen goes in the middle. Hydrogen will never, ever, ever go in the middle. But it's the least electronegative, so I'm just going to start bonding hydrogen around. There's the bell. And I've used up 6 electrons. So nitrogen is going to take the last 2. That way each hydrogen has 2. Nitrogen's got 8, so everybody's happy. Carbonate. All right, so carbon's got 4 valence electrons plus 3 oxygen, and each oxygen has 6. And then we've got to add in our formal charge. So 2, so 6 and 18, 24. Okay, so carbon, I'm just going to add my oxygens around carbon. Okay, so I've got 2, 4, 6. I need 24. So 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, I've used all my electrons. All my oxygens have 8 valence electrons around them, but carbon, 2, 4, 6, only has 6. He's not happy. So what happens is one of these oxygens, I'm just going to pick this guy right here, he's going to have to share these electrons. So I'm going to erase those 2 and double bond. So now carbon's got 2, 4, 6, 8 around. Each oxygen has 8 around, so he's happy. Since this is an ion, I have to put brackets in the charge. Now, I could have put the double bond here or here. That means I should have drawn resonance structures. So this is just very crappy because I would run out of room anyway. But I would have to show all my resonance structures. Intermolecular forces. Okay, so there's 3 types of intermolecular forces. The first 2 are called van der Waals forces. London dispersion, this is between nonpolar covalent molecules. Dipole interactions, that happens between polar covalent molecules. These are very weak. They're all pretty weak forces, but these 2 are the weakest. Hydrogen bonding is going to be the strongest of the intermolecular forces. These are between covalent molecules that have a hydrogen attached. So, water. And really, hydrogen bonding can only occur between if there's an O, an F, an S, or an N attached to it. Only these will hydrogen bond. So hydrogen bond is very important. It's what holds your DNA together. So those forces have to be strong, otherwise we wouldn't exist. Also, water is polar, right? It has a bent shape like this, 2 lone pairs, and that makes it very special. It has a high surface tension. So if you look right here, when their molecules are stacked and you get these hydrogen bonds in between, it makes the surface of the water very strong. That's why it hurts really bad to belly flop into a pool, because you're breaking that surface tension. That's why these little spiders can skim across the water and not fall in. Surface tension, because of hydrogen bonding. So you need to remember water is polar, it's bent, and it has high surface tension because of hydrogen bonding. So this hydrogen bond, what I'm talking about, is right here. It's between the molecules. This hydrogen is attracted to this negative oxygen, and you kind of create almost like a fake little bond. When water freezes, water is very special. Unlike other molecules that shrink when they become solid, water expands. And if you can kind of see, so this is ice, so this is frozen water, right? Solid water. It forms this honeycomb shape. You get these little pockets of air in there. This is why ice floats. And if ice didn't float, you'd have no ocean life because it would all freeze. So this honeycomb shape and the fact that water expands due to hydrogen bonding is very special.